Good evening, everyone, and welcome to North Penn High School. It's good to see all of you. My name is Mike Boyer. I'm a technology and engineering education teacher here within the Engineering Academy. And tonight, I'm so excited to share with you the research of 5 research teams that I've been working with this year. And I've had the awesome opportunity to learn alongside of them with some of these amazing endeavors that they've been joining in. To get started this evening, I thought it would be a good idea to talk a little bit about the background of our program, just so that way you have an understanding. There are some new visitors here that might not be familiar with the Engineering Academy here at North Penn High School. So I'll take a few minutes and then we'll go through a little bit about what we do, and then we're going to have 5 research teams come up and present for a few minutes about their research this evening to you. When they're done, we're going to head up down to the auxiliary gymnasium, and you'll have the opportunity for them to actually give live demonstrations of all of their work that they've been performing this year. You can ask them questions. It's completely open-ended, informal, and you just have a good time. Oh, and there will be some snacks there too. All right. So anyway, at North Penn High School, we started an engineering academy in 1999, and we wanted to open up the opportunity for students who were graduating from here and wanted to get into engineering, but never came down to the tech ed department to learn about any of the skills and things that we offer here. So we decided to start an engineering program that has a 5-course sequence. And the first 4 courses are usually taught in the sophomore and junior year, and then their senior year they take a capstone engineering courses, which is what these students are involved in, called Engineering Design and Development. So it's the senior capstone course of the Engineering Academy. They follow throughout this year a 6-step engineering design process, depending on which university you go for engineering. It could be 12 steps, it could be 8 steps, but they all follow the same general idea of defining and justifying a problem, taking a look at what other people have done, so prior art, prior research, and then they look at ways of, well, how can we design something that's better on the market that we can work with. They construct prototypes, they test them, and the most amazing thing we've had this year is a grant from Dow Chemical that has given us the ability to get some really high-quality research characterization equipment to be able to measure some serious superconductor nanofibers and all kinds of other things that we'll share with you this evening. Oh, and step 6, present the results. That's where they are this evening. How did nanotechnology get into North Penn High School? You won't find other high schools running a nanotechnology program like this. This is not something that came along with Project Lead the Way or something we found on the internet. This came from an experience that I've had while working at Drexel University. I applied for a summer research program in 2003 and worked with this professor here named Dr. Frank Coe, who is now at the University of British Columbia. But he and his graduate students taught me about nanotechnology, and he sent me this paper to read in the abstract, which I won't read all of it to you, but if I read to you the first sentence, ultrafine fibers of polyaniline doped with camphor sulfonic acid blended with polyethylene oxide were prepared. I read that far and went, oh no. I had no clue what this paper was about. I was nervous. I'm looking at this, and I said to my wife, I said, honey, I don't know if I can do this program. I got accepted, and I can't believe I got in, but I don't know what this professor just sent me. And she's like, well, how would your students feel if you gave them something, and they said, I can do it? So I'm like, you're right. So I'm really thankful that she pushed me, because I ended up going to Drexel and working and learning about the nanotechnology process. I learned about material science and the fact that, and it's something we kind of take for granted, everything around us is made of materials, right? But what do we do with these materials? How do we modify them? What can we do with them? When you think of car tires today versus car tires back in the 1900s, back when the Model A's were around, completely different. And that's all because of material science. That's because of engineers and dreamers and thinkers who say, there's got to be a better way to do this. And so that's where these students are tonight. They're thinking, there's got to be a better way to work with the materials we have. And so we learn about material science. And we learn that it's an investigation. We look between processing, structure, properties, and performances of materials. How do we change them? How do we modify them? We take a look at, in this example, every single vial has gold nanoparticles in them, but they're different color. But it's all the same particle. The only thing we changed was the size. So if we change the size of something, energy interacts differently with materials. Why and how does that happen? And that's what these guys do. That inquisitive nature that yearning to be autodidactic, to feed your own knowledge without waiting for somebody to tell you is what this program has really opened up for these students. And for me, I learn every day and I love it. They learn about thermodynamics and taking a look at different forces. Temperature is a force, heat is a force, it's an energy. Mechanical forces we think of all day long, but also magnetism. And I don't know if you've ever thought about it, but light is a force. Do you get a sunburn when you go outside without sunscreen? Many people do. That light is a force. It's changing the properties of our skin. So we use titanium and nanoparticles and other materials to reflect that UV radiation. There's got to be a better way to get still. And we're working on that next year. So what forces can we apply to our materials to change its properties so that it can do what we want it to do? And that's what I ask them every day when they're doing research. Well, what forces are you applying? What are you doing? What's happening to the material? Always ask. Don't just take it for face value. So then we talked about nanotechnology, and I introduced the students to nanotechnology, and nano is a Greek word meaning dwarf, or small. And this is a picture of a dwarf standing on the shoulders of giants. These students in September were dwarves. They were reading papers like I was reading and not having a clue and being like, oh my gosh, what did I get into? And now they're giants because all of their research they can share with next year's students who will be dwarves standing on their shoulders. There's nothing more exciting than that, to see that knowledge being passed on. It's really, really cool. So nanotechnology is the creation of functional materials, materials that have a purpose, devices and systems through the control of matter on a nanometer length scale. All right, so what does that mean? And then we exploit these novel properties or new properties. So a nanometer is 1/1000th of a meter. Can you imagine a billionth of anything? So if you took a piece of string and cut it into a billion pieces, you took 1/1000th. That's the scale these students are working at. It's absolutely phenomenal. It's amazing to have the opportunities, all of us, to do this. It's exciting. So if we take a look at some things around us, some common things around us, a head of a pin is 1,000,000 nanometers. Yeah, that's crazy to think about. Your red blood cells, 5,000 nanometers. Visible light, 390 to 700 nanometers in the wavelength. So when we're working with materials smaller than the wavelength of light, you can't see it. It's smaller than one cycle of light energy. So we can't use an optical microscope to characterize nanofibers. We have to use something else. How do we see at the nanoscale? We use something like this, a scanning electron microscope. We don't have an extra $1 million laying around. I've been trying. I've been really trying to find that money. But we can't. So we can't put a piece of equipment quite like this in our lab. However, we've paired up with Hitachi and a company in northern New Jersey called Angstrom Scientific, who has so graciously, for the past 5 or 6 years, have lent us a scanning electron microscope to use in our lab so these students can characterize their nano work. It's insane. It's awesome. And I sit down, they're running it better than I can. It's like, oh, it's words, get out of the way. I can run this. And they understand that how this scanning electron microscopy actually works. So the next thing that I learned at Drexel and that I teach with the students is a process called electrospinning, where we're taking a high voltage, anywhere from 0 to 30,000 volts. Sounds like a lot, however, the current, which is the amount of electrons that are pushed, is very low. So we're talking 5 watts of power. Your cell phone has more energy than this power supply up here. But we use a high voltage to cause a polymer to jet out of a syringe and land on a collection plate. Do you see this white circle? Those are nanofibers. Hundreds of thousands of nanofibers or more in that small area, and they were generated within seconds, and the cost to make these nanofibers, pennies. So you say, well, what can we do with these nanofibers? Well, here's what they look like to the naked eye. Here's what they look like under an electron microscope. We can analyze the surface. You say, well, what if the surface were rough? Maybe we can use it as an air filter to trap dirt particles. Maybe we can align these fibers, and if we bring them close enough, we can make better HEPA filters. So we can filter out viruses and every airborne possible contaminant that we can think of, which would be awesome. Use it for water filtering, blood filtering, and we can go on and on and on about potential applications. So I fell in love when I was at Drexel with research. I couldn't believe it. I'm like, how am I going to get my students to get involved? What can I do with this? And so I started looking for grants. And I wrote for several grants my first year, and while I was at Drexel, I also wrote the engineering design curriculum, the nano curriculum, And these companies so graciously, collectively gave over $20,000 to start the program in 2005, 2006. It was awesome. And from that, we're still using that money today and that equipment today in our labs, still today, which is absolutely fantastic. Now, where have we gone and where are we going to? Just a little bit more background. In 2005 is the first year we started. So back then when we were looking at the electrospinning process, the students were like, well, what happens if we change the voltage? What would happen to the fibers? That was their question. And if we look at this one particular student here, is he in the audience? I don't know if he's here tonight, but his name is Mike Noche, and he was here in 2005. Now, if we look in 2015, 10 years later, it says, how can we prepare these polymers to successfully alter their structure to create an e-textile, an electronic cloth, so we can wear our electronics and not have to carry them around. And this person here is his brother, 10 years later. This is Alex Noche, which you'll see up here on stage, which is kind of cool. So I'm pretty excited about that. Now, if we take a look up here, these are some of the awesome opportunities that we've had, and I want to start off with a quote for this discussion here really quick with you. A vision without resources is just a hallucination. So a vision could be an idea, a dream, a goal, something you want. And then you think of resources, most people think of money. I don't have enough money, I can't. But you can also think of time, experience, knowledge, experts in the field that can help you. And for our students this year, it's been unbelievable. This year we were fortunate, very fortunate, to win a $30,000 STEM grant from the Dow Chemical Company. And a grant writer contacted me over the summer, Valerie Vastine Orbell, pardon me, Valerie. She contacted me over the summer, and long story short, we applied. She goes, let's do this, I think we're going to get it. And guess what? We did. And I'm very thankful for Dow because I just want to do nothing but please them and honor them for the talent and the money they've given to us because we've done a lot with it and can't wait to share it with you this evening. Actually, one of the other resources, not just money, is talented engineers. So up here we take a look at Dow Chemical sent out several engineers to meet with my students back in March to actually interview with them. The students presented their research to them live, right in the classroom, and share with them, and the engineers said, hey, we have some ideas, maybe you can do this, or what did you ever think about doing this? And it was really cool, open, collaborative dialogue, so I was pretty excited. One of our research teams did antibacterial research this year, and we worked with Dr. Lori Dodson over at the North Monaco Technical Career Center. She worked with the students over several days and gave them the opportunity to test their nanofibers against E. coli and several other strains of bacteria, which is awesome. I'll share that with you this evening. We also had EDS manufacturing, which this gentleman here is my father-in-law, and he has machined a device for one of my students. If you look here in the center, one of my students developed and designed an apparatus to electrospin to a rotating disc, and my father-in-law actually machined it for them, and you'll see that tonight, and I'll talk to you more about that as well. And then just 2 days ago, we had received back some nanofibers from one of our research teams who actually electrospun superconductive nanofibers, which is rare. There's very few people, nobody in high school ever does this. But even in collegiate university level, you're not seeing quite this level of research. And these students, the next step was, well, now that we make these nanofibers, we have to put them in a furnace. And we have to heat them up to 900 C, is that right? 950 C, Celsius, for 16 hours. Where are we going to find a furnace that goes up to 950 degrees Celsius for 16 hours? I don't think I can ask the art department or, take it to where I have a toaster oven in the back room that says for research only. I don't think we can do that. So we met with Dr. Michel Barsoum and one of his undergraduate students, Cooper Voigt, and they so graciously said, not only will we do this for you, but we'll get it all set up and then you just come pick it up and be ready to go. They ran the fibers we got up today, and I don't want to give anything away, so I'll let the research team talk to you more about it. But this is awesome. And I have to say, when they called me, I was still at school working with these guys on the presentation. I'm like, I couldn't get down there until about 6 or 7. So I called my wife. I'm like, honey, what are you doing tomorrow? She drove down to Drexel, picked up these fibers for us, and I feel so thankful that she was able to help us out. So that was really cool. So again, it's definitely a team effort with all of us. But very cool with Drexel University and the research that helped us. And I cannot say anymore other than the North Penn Educational Foundation has been so gracious every year to help out our students with their research endeavors. Without them, it wouldn't be possible to do half the things that we do. So I want to make sure that I honor them as well this evening and let them know that their work for us and their donations to us are so graciously appreciated. So it has been an amazing year. You kind of see where I started and where we're headed now. What I'm going to do is hand it over to the students, and I'm going to let them share with you a little bit about their research tonight. We'll have 5 teams, and then we'll go down to the gym. Thank you very much.
Hello, I'm Jordan Van.
I'm Alex McKay.
And I'm Connor Sloan, and we are Electrospinning. Hey guys, I noticed something.
What's that, Connor?
Everyone, 100% of the people here are wearing clothes tonight.
That's a great observation, Connor.
You should be researcher. But I think chances are the clothes you're wearing are at least integrated with today's technology and all that you interact with today. And let's face it, clothes that serve the same job for human life, protection, and we want to change that.
Google also has the same vision with Project Jacquard that they launched about a week ago at their developer conference. They were looking into embedding metals into average fiber batteries and getting it to communicate with cell phones, computers, and stuff like that. If you take a look at Connor's pockets where that is a conductive fiber or battery that we will be demonstrating some properties on the auxiliary gym. We did this through a process called wet spinning instead of embedding metals into the actual fibers.
So, as Joe just mentioned, we did a process called wet spinning, and here we have a little drawn-out diagram of the process, basically. So what you see on the right-hand side is a syringe with a polymer solution, and that's really the fiber that's going to be produced during the process. And in the coagulation bath, that's going to be a chemical solvent, and that's really imperative in creating a fiber or a film in the process, and that's a really important parameter that we have to look into to actually produce our experiments. And so here we have a quick 7-second clip of us actually doing it. You'll see the syringe on the right-hand side of the screen, and the black string-like rope is the fiber.
So that video was one of our first experiments, or one of our more recent experiments, but this is an image of our first experiment that was successful, which was a polymer called polycaprolactam, and we spun it into a bath of water and calcium chloride, which were 2 chemicals that we had readily available in the lab. And this is actually an image of the second attempt we had. The first attempt turned out like a film, sort of like a plastic bag, and the second time we did it, we changed the needle gauge, and it gave us a good virgin-like fiber. After a while of researching, we learned about a polymer called polyacrylonitrile, or PAN, and it's a precursor to carbon fiber. And a lot of papers said that it was very useful in the process of wet spinning. So we moved on to that, and we did a lot of experiments with it, and every time we used it, it came out really nice. And in this image, you can see we used blue food dye on it to make it more visible. So usually it's a clear yellow color. And the most recent polymer we worked with is called polyethylene diacetylene polystyrene sulfonate, but that's a mouthful, so we'll just call it PDOT. And it's an inherently conductive polymer that is difficult to wet spin with because it sticks to the bottom of the glass beaker that we use. But you can see it in the middle of this SEM sub, which is how you mount the sample into an SEM. And it's a little flat line in the middle of the aluminum floor.
This is an optical image of polyacrylonitrile. This is showing the air bubbles that are formed inside the fiber from the wet spinning process. If you take a look to the bottom right corner, you'll see the scale bar showing that the fiber is approximately 400 microns in diameter, or about 4 times the thickness of human hair. And this is a picture of PDOT embedded inside of the PAN fiber, and the blue that you're seeing is actually the PDOT that's in the fiber, that's the light shining through it.
So So our first experiments, we used polymers that weren't inherently conductive. So what we had to do is we had to embed other conductive materials in them to actually get conductivity value to read from them. So what we chose a pretty well-known conductor in copper. And so that's copper nanopowder on the left in the small vial. And then we used the polychrome nitrile as our carrier polymer in our experiments. And we used 3 processes to actually get samples. The first process we used was wet spinning. And so you can see the fiber there, that's an optical microscope image. And the black specks in the fiber is the nanopowder dispersed throughout. And then we used another process called spin coating. And Alex will have more information on that pretty shortly. And what that is, it creates a thin film on a glass slide, and the black dots there are also the nanopowder dispersed over a thin film. And then we also electrospun our samples, so we have a nanoscale sample and a macroscale sample. And those are the 3 we did.
As Connor mentioned a moment ago, one of the processes we use is called spin coating. This is our spin coating apparatus that was developed by Phil Research team, Nanotechnology, and in our case, it's a modified centrifuge that spins a glass slide at high RPM, and it creates a thin film of whatever material we decide to deposit. So we used it in our experiments to find an optimal blend of PDOT and additive to find what would have the highest conductivity for future testing, as it requires little solution to use, but it gave good results.
And these are some of the glass slides that we produced through the spin coater. And you'll see on the very far left is just PDOT on a glass slide. In the middle is PDOT embedded with multiple carbon nanotubes. And on the right is PDOT embedded with copper nanopowder. And this is a dark field image showing the PDOT on the glass slide. There's not really much to see because it's just a thin coating on there. But if you looked, it is a blue tint. And these are the multiple nanotubes, and you'll see that they're not as evenly dispersed as the copper that we want to show you. That is, they're there. And this is the copper, and this is more even dispersion, but still not as even as the PDOT by itself.
So as Mr. Boyer mentioned in his segment, this is a senior capstone course, so we only have 1 year to work. So it's kind of hard to accomplish everything you set out to do in the beginning of the year. So if we were to have more time to continue research, we would look for other additives to further our embedding experiments in wet spinning.
And another research goal for the future we have is to get a better understanding of bath chemistry in wet spinning, because the bath chemistry is one of the most important factors in determining whether or not you get a fiber, a film, or ribbon, or nothing at all. So knowledge of bath chemistry would allow us to get fibers that have the desired physical property that we want.
And by developing more innovative applications for our findings, we could open up the rest of the world to the advantages of conductive fibers and further research.
And we would also look into getting some inherently conductive polymers to spin, because then we wouldn't have the need to embed other conductive materials in there as a parameter, so we were able to expand our options. And that's all we have. Thank you for listening. And next we have BCC Biotech.
People die each year due to resistant bacterial infections. For BCC Biotech, I'm Cameron Benjamin.
I'm Justin Craig.
And I'm Connie Conley.
2 million people each year are affected with resistant bacterial infections. Any blood loss over 20% in an adult can result in cardiovascular function failure. So this year, our group decided to research wound care.
When we first started our project, we didn't quite know which direction we wanted to go. We knew we wanted to create a product that could be used for large units that had excessive blood loss. We wanted to create a product that was better than the ones on the market, so we thought that by combining aspects of the antibacterial and absorbency, we could.
The current products on the market include Betty gel, which is a gel that's directly injected into the wound. We have a syringe where it absorbs the blood, it expands, which puts pressure on the walls of the wound to stop the bleeding. Wound seal, which is a powder that's applied directly to the wound and pushed into it, where it absorbs the water out of the blood to dehydrate the blood cells, where potassium ferrate then coagulates the blood to create a stab. X-Stat and X-Gauze are basically the same thing because they're made by the same company. They're basically super absorbent sponges that you inject with the X-Stat into the wound, where they absorb the blood, and as they absorb, they expand to put pressure on the wound. The X-Gauze is basically the same thing, except it's in a different form. It's these sponges that are encapsulated inside a gauze sort of case. They can be wrapped around the wound or cut into sections and then taped over the wound. And as you can see in the bottom picture here, we have a before and after of the X-Gauze to show how much they actually absorb.
In order to create an antibacterial polymer, we had to research 3 materials that had antibacterial properties. Chitosan, which comes from crustaceans, had no visible effect on the bacteria, while silver nitrate and silver nanopowder did have visible killing effect on bacteria.
Our antibacterial testing consisted of using 2 types of bacteria. We used E. coli and Escherichia marcescens. We took our proposed solutions and tested each one along with their components to compare their effects. We looked at their zones of inhibition, which are the areas around it that showed no bacterial growth, and then from there we finalized our solutions that we would use in the future.
For the absorbency portion of our research, we used regular gauze that you can find at any drugstore or something. Then we used gauze embedded with PCL and sodium polyacrylate, which is the super absorbent powder that you find in a diaper. And then we also tested gauze with just plain PCL to make sure that the PCL and our sodium polyacrylate the sodium polyacrylate piece, so it wasn't messing with the data.
To test our samples for absorption, we electrospun our solutions to the gauze, then we submerged each gauze sample in water for 30 seconds. After that, we put the gauze and drained it using 400 and 800 gram weights on our homemade apparatus. Our results showed that our solutions did nothing to increase the absorption capacity of the gauze.
If time allowed, we would have researched more solutions to use for the absorbency aspect of our project, which we would then hope to combine with our antibacterial solutions to create our final product that is not only better than what's on the market now, but also much reliable and cost-effective. Thank you for your time, and we'd like to hand it off to Dr. Solutions.
Good evening, I'm Christopher Seibel.
I'm Jacob Boyce. And I'm Jack Peckham, and we're Nantech Solutions.
Now, a lot of you probably watch the news every morning and see a report of maybe a new breakthrough for cancer research, or something new that you might be able to use in your kitchen, like a new type of artificial sugar. You may ask yourself, why don't I see those products in the store? And the truth of the matter is, research is difficult, and it's even more difficult to get discoveries out into your everyday world. And that's the problem we as Nantech Solutions want to solve. When we first started learning about electrospinning, we learned that 90% of your initial solution is wasted due to evaporation. Now, when electrospinning on a small scale in school is not the biggest problem, but mass producing nanofibers is very difficult, and wasting 90% of your solution can cost a lot of money. So we asked ourselves, how can we fix that? And the solution we found is going back to the lessons that Mr. Boyer taught us about materials engineering and how we can use forces to change the way material behaves. So if you look up here, I have a cake, and it's only missing one key ingredient. We have flour, sugar, eggs, butter, vanilla, and milk. But the one key ingredient it's missing is heat. Now, as you can see, with a little bit of heat, you can turn all those ingredients into a cake. And like that, our research uses heat to change the material and make it more useful. Instead of using a solvent to dissolve our polymers, we actually heat it up to turn it into a liquid, to electrospin.
Now, we were the first ones to come up with electrospinning, but there were some distinguished universities like Harvard University, some local like Drexel and State, and some foreign universities like the Queensland University of Technology, who see electrospinning as a viable research option for them. Now, it's been a long journey to get here. We started in the beginning of September to here today. And the first step in electrospinning is creating a setup. Now, this is a thermal regulator, and we had some problems with this at first as it interacted with a high voltage power supply, which created a shortage, which we couldn't get the background and out of voltage in order to electrospinning. And this is a picture of our first setup, where we placed the polymer on the syringe and wrapped it, heat tape around it, and connected it to the thermal regulator, which applied the force of heat to the polymer and syringe. But soon we realized that polymer that we used was too viscous to use and would not flow out correctly, so we decided to need a new setup to use.
Now, as Jacob said, our original setup had its problems that we needed to solve. And it wasn't until the second to last day we had the SEM that we were actually able to build our first working melt spinning apparatus. As you can see, this is a picture of it. The two biggest differences is that this one uses a heat gun to heat up the polymer instead of heating tape, and the second is that it uses a copper wire to transfer the voltage throughout the polymer. This is one of our first samples of hot glue. As you can see, the alignment is quite random on it. And we thought, how do we make the fibers go in the directions we want them to? So we built this setup. This one uses a copper tube to melt spin the fibers onto them. And as you can see, the white lines across it, those are the fibers that we spun. This is one of our samples underneath an SEM, hot glue. As you can see, the diameter is all roughly uniform throughout the fibers. A closer up picture reveals that the fibers are only about 30 microns in diameter. And a couple of weeks after the hot glue, we also managed to melt spin PCL, and this is a PCL underneath the Zeiss optical microscope. And this diameter is only about 3 microns, much smaller than human hair. So we keep talking about melt spinning polymers as the fibers, but what can we use those for? Well, they're high strength polymers. So anything that's higher strength would be better in making materials. And not only that, the diameters of our fibers were also much smaller than the industry standard, which means we make more intricate arrangements, which would be useful in processes like 3D printing.
Now, electrospinning can be applied to all areas of the textile industry. As said before, electrospinning fibers are high strength, and so they can make durable clothes so they don't break or stretch easily as regular clothes. And also that the fibers can be small and very complex structures, so they can repel liquids that fall into the clothes. Now, we are really standing on the shoulders of giants and improving upon the traditional electrospinning setup and textile industry processes.
You know, as my peers before shared, it's very difficult to research in high school. But if we were given the opportunity, one of the first things we work on is improving our apparatus. As you can see, wire wrapped around a hot glue stick isn't the most accurate of designs, but it's functional. But if we were able to have more time, we would definitely try and get a working apparatus that was a little bit more functional. Also, we work with BCC Biotech and use polycaprolactone, which is also biocompatible, to help make them make bandages that would be able to help their research and ours. Or we could research with electrofiber and melt spin conductive polymers and then coat them with other polymers in the wet spinning process to create wire-like fibers that can be used in multiple industries. And that's all that we have for you tonight, and now BCS Technologies. Thank you.
Hello, my name is Jay Benmar, and I'm Nick Klein, and our team is BCS Technologies. Now, this is a list of numbers, and they're organized from the highest number to the lowest number. But they mean something. This is the loss of value of energy per megawatt hour, because of some of the most common overhead power line conductors, like you see outside of the pylons, the overhead conductors by the roads. When they first started installing these cables to connect homes and places of business to power stations, they used copper because it was a very well-known conductor. But they found that because of the innate resistance in copper, caused a loss of electricity the longer the wire was. And so that led to $24,000 per megawatt hour. And technology has improved over the years down to the most recent all aluminum alloy conductors. But still, $8,600 per megawatt hour is a significant loss.
Now, with a significant loss, you don't want to be paying that at all. So the Holbrook project in Long Island set forth to prove that wrong. And here you can see them installing superconductive wires into the ground to power multiple homes within the vicinity. And right here you'll just see a cross-section of the wire and how it needs a coolant, such as the nitrogen, to keep the proper components cool.
These wires work off of some unique materials called superconductors, where they have no resistance at below a certain temperature. And so that's what we were looking into. And we found two very long-named materials that we wanted to look into. Yttrium-barium copper oxide, or YIBCO, and bismuth strontium calcium copper oxide, or BISCO. Now, the company American Superconductor, when they put it in those power lines, used BISCO, because although the reagents to make the material are more expensive, the processing techniques that were in place at the time made it a more economically feasible material to make these cables out of. But we thought, because electric cables are very thick, because they need to overcome that innate resistance. But with a superconducting material, it can be at the nanometer level scale in diameter and carry the same amount of electricity. So we looked into electrospinning YIBCO.
Now, with our research for finding just papers on this, we found none for BISCO, but we found two papers for yttrium-barium copper oxide, and both papers had in common a spinning disk collection medium, which we have here in our lab, but with frayed wires and a uncontrollable motor, it had many issues.
Yeah, when we were electrospinning, there was a charge interaction between the DC motor and the high voltage power supply that caused the motor to spin at irregular speeds. And these triangle brackets that we designed and 3D printed, the fibers seemed to lay just over them and not on top of the collection plates. But we got some very valuable data from these tests, these initial tests. We found through using the scanning electron microscope that the nanofibers we were forming were very well aligned, as you can see here vertically. And this sample was taken from the edge of the disk, where multiple fibers had laid on top of each other. And you can see that even after being manipulated, the fibers that make up this cable maintain their relative alignment.
Now, when we saw our first disk, we just didn't want to use it. So we went ahead down the path of making a new one. And that's when supporters Father Long came in, and we asked him to make us a disk.
And he surprisingly agreed.
Yes. But we wanted to SEM studs and also 1 millimeter by 1 millimeter substrates of any sort. And with that, we also create apparatus, which consists of pillow blocks, bearings, collars, and what's running is a stepper motor that's controlling it at proper speeds.
And from some initial tests, you can see, even at the macro scale, that there is fiber alignment between the surface of the disk and, in this case, a glass microscope slide that we're spinning to. Our next problem that we had was recreating these solutions. You probably don't know this, but YIBCO requires with the electrospinning process, requires very dangerous chemicals. So not only do we have to do all of our work in a fume hood around the chemistry department schedule, but if we wanted to make any changes, it was very difficult to find time to make another solution. So we only ended up making 2 solutions. The one on the left being exactly replicating, to the best of our ability, the paper's parameters as to weight densities for the YIBCO and the carrier polymer, in this case, PAAC, polyacrylic acid. But that didn't electrospin very well, we thought. So we made a second solution, which had a greater concentration of the YIBCO, which we hoped would result in more definitive fibers. And these are some optical microscope images under dark field. And I'm not sure if you can see very well, but there are very faint lines connecting a bunch of little specks. And we believe that those very faint lines are the PAAC carrier polymer holding together YIBCO particles.
Nick, did you see those up there?
I did, in fact. This is a Google searched YIBCO superconducting graph.
Why?
Oh, well, surprisingly in research, you need expensive equipment. And like Mr. Boyer had mentioned, most people won't lend you their multi-$1,000 piece of equipment for an extensive period of time to high school students. So we were only able to get our finalized samples 2 days ago. And surprisingly as well, it's difficult to find liquid nitrogen.
Really?
Yeah, I know, right? And so, unfortunately, we have not been able to test our samples. As you can see here, 92K is the highest, the average critical temperature, of YIBCO, which liquid nitrogen is about 77K. But we have been able to get some preliminary results using dry ice, which is significantly higher temperature. But we found that when we graphed the temperature versus resistance graph like this, we got this bit. So that's promising. And I've run an SEM analysis on our finalized fibers. We should be able to determine if they will likely superconduct. On that note of not having time, we were very optimistic during the beginning, weren't we? We were like, yeah, we'll replicate this paper, and then we'll do all this other stuff. And we never got to the other stuff. But we hoped to continue our research, we hope to electrospin BISCO using a similar process. We didn't find any papers on electrospinning BISCO, so we would be interested to see, with using a similar process, if we got similar results. And also an idea that was brainstormed during the Dow Chemical Engineer visitation was to suspend particles of superconducting materials in a carrier polymer to see if the superconducting state could overcome the resistance of the polymer that it was in.
Thank you for listening. That's all. We'll be handing off to Nanotechnologies.
Good evening, everyone. We are Valence Technologies. I'm Brandon Berlin.
I'm Old Ricky.
So I believe many of you recognize what you see on the screen right here. It is an electric bill, and for many of us it can be very rough. What if I told you that we could change this to cash in your pocket?
So one way to reduce your electric bill is through photovoltaics. Photovoltaics are a semiconductor material that takes in light energy and turns it into electrical energy. And certain materials that exhibit photoelectric effect can be manipulated into use for solar cells.
One type of photovoltaics are silicon-based solar cells, which are commonly used today and can be found in many homes. However, these have an expensive and complex manufacturing process. Another type of photovoltaics are solar concentrators, which uses lenses and mirrors to concentrate sunlight to harvest more energy. These can reach higher efficiencies, however, they require a lot of maintenance and an extensive plumbing system. One example of cutting-edge research done in photovoltaics involves the usage of quantum dots. We would have liked to have some research on quantum dots, however, we found the materials to be expensive and toxic.
After researching the different types of solar harvesting, we decided to research dye-sensitized solar cells. And these basically are a thin layer of titanium dioxide on a glass slide that, through chemical processes, we can convert UV light to electricity.
So through our research, we found that the DSSC is the most promising. We decided to invest all our time into manipulating the TiO2 layer, and we did this by fabricating new novel methods of creating TiO2. We also researched on solid-state electrolytes to increase the lifespan of DSSCs.
So one of the processes we used to fabricate our titanium dioxide slides was spin coating, in which we deposited a precursor solution onto our conductive glass slide. Spinning at high RPMs, a thin film of titanium dioxide was formed onto our glass substrate. This is a dark-field image from our Zeiss microscope of our glass slide, and as you can see, the titanium dioxide is well dispersed. We also electrospun the precursor solution to obtain titanium dioxide fibers. This is an image of our fibers on the SEM.
To analyze our samples, we created a photoelectrochemical chamber that tested the light scattering ability of our TiO2 nanometers. What it is basically was 5 UV LEDs and 4 photoresistors that measured the reflection of the light off of our samples. We used multimeters to register the resistances of each resistor and to calculate the outward voltage and current of our TiO2 nanofibers. Using a key source meter, we were able to create IV curves of our samples and also test the resistivity of the TiO2 layers.
Concurrently with researching TiO2, we researched on solid-state electrolytes. Originally, DSSCs have a problem. So the dye and the electrolytes usually dry out and short-circuit the whole current of the whole solar cell. So we decided to research how we can make our electrolyte into a quasi-solid state. And we did this by incorporating sodium polyacrylate, superabsorbent polymer. And we made separate samples to test how sodium polyacrylate impacts the electrolyte resistance.
In this image, we are assembling our final DSSCs. We are adding the electrolyte solution to our glass slides, which will then be sandwiched together and held in place by binding clips. We found that the spin-coated samples produced a greater power than the electrospun samples, and among the spin-coated samples, we found a deposition volume of 0.5 milliliters to produce the most power. In our electrolyte studies, we found that this addition of the superabsorbent polymer decreased the conductivity of our electrolyte solutions. Therefore, in our final DSSCs, we use an electrolyte solution that contained no sodium polyacrylate.
So if given more time, we would like to invest more research into creating vertically aligned titanium dioxide nanorods. This will help study the morphological impacts TiO2 has on solar cell performance. We would also like to research multi-junction solar cells, as they are the next technology for solar cells, as they absorb more rays of light. In addition, we'd also like to research organic solar cells and incorporate conductive polymers such as PDOT into our photoanode layer.
I would like to thank everyone for coming out tonight, and we're going to hand this over to Mr. Boyer for some closing remarks.
Good evening. Back again. All right, so tonight I'd like to introduce, oh no, that was earlier. No, I'm just kidding. Wow, I am really, really excited that they were able to share with you and for you to be able to see the research that they've been performing this year. For me, it's been absolutely amazing because a lot of what they were doing, I felt like my first research paper I was reading. I'm familiar with some of this, but there's some I need to research. And so I'd be spending hours at home digging in and having my own research journal alongside of the students. And we were kind of working together as research colleagues. I feel so blessed to have this opportunity to work with them and to be able to do what I do every day. There's nothing more rewarding than growing and learning together and being able to see the fruits of your labors just develop over time. So I'm really excited for these seniors, and every single one of them in a week and a day from now will be graduated North Penn High School seniors moving off to their engineering universities that they've all applied to. So I'm really, really excited for them. Could we just give them a quick round of applause again, please? I'd like to just bring them up the stage so you can see the senior class of the North Penn High School Engineering Academy at this time. And if anybody wants to take a picture of the whole group together, you can do that while they're here. It's been an amazing journey this year. Really exciting time. You guys can all come out and should be able to fit across the stage. Again, I'd like to thank you all for coming out this evening, and we're not done yet because now you're going to see the true magic and the true research by going to the gymnasium where they're going to have research posters. Exactly what you would see at any engineering university, and they're going to be presenting their research to you from these posters that they've developed and prepared. There will also be demonstrations as well as snacks and food and a live demonstration of a scanning electron microscope this evening. Thank you so much for coming out this evening, and we'll escort you out the hallway here down to that direction to the auxiliary gymnasium. Thank you so much.